Good morning, everyone. I'm delighted to present our research paper titled Exploring Sentiment Patterns in ChatGPT Interaction, a Machine and Deep Learning Approach to Sentiment Classification at the International Conference on Smart Computing, IoT, and Machine Learning 2025. Our research team consists of myself and Jonathan, Cornelius, Karel, Halim, Lily Ayu Wulandari, and Gina Zain Nabila. Next, let me elaborate on the critical background that motivated our research. We identified two key areas that demonstrate the significance of understanding sentiment in AI interaction. First, regarding human-AI interaction in high-stakes domain, recent research by Palai and colleagues in 2023 revealed a concerning trend where ChatGPT has provided incorrect or fabricated information in medical research contexts. This highlights the crucial need for human oversight and precise sentiment analysis to ensure reliable AI interaction in critical fields. Furthermore, Hormats et al. 2023 study uncovered how subtle discrepancies in sentiment interpretation can lead to user disengagement or maladaptive reliance on AI systems. This finding emphasizes the importance of improving sentiment analysis to help AI systems better understand and respond to user emotions, ultimately fostering trust and meaningful engagement. Second, looking at the economic impact of AI adoption, a very recent study by Go in 2024 provides fascinating insights into how public sentiment towards AI technologies directly influence organizational implementation rates and adoption trajectories. The study found that positive sentiment can accelerate AI adoption, while negative sentiment can create barriers, ultimately affecting economic growth. Additionally, Lee and colleagues in 2023 proposed a framework specifically focused on advancing AI explainability in government agencies. Their work emphasized the critical role of understanding public sentiment in ensuring responsible AI deployment. By enhancing sentiment analysis tools for ChatGPT, we aim to bridge AI capabilities with emotional intelligence, enabling more reliable AI implementation across sectors. Next, moving on to our literature review, we've identified two major areas that inform our research approach. First, regarding sentiment analysis in ChatGPT interaction, prior research has primarily focused on sentiment analysis across social media platforms like Twitter and Reddit. While valuable, the study have typically concentrated on general sentiments toward AI technologies for specific applications such as customer service and education. A notable study by Hack and colleagues in 2022 examined early adopters' sentiments toward ChatGPT on Twitter. However, their research didn't delve into the conversational context or the subtle emotional nuance that occur during actual user interactions. This gap in the literature is precisely what our research aimed to address. Second, concerning the benchmarking of machine learning and deep learning models, the current landscape shows that many studies have taken a somewhat limited approach in their model comparisons. They typically focus on traditional models like logistic regression, LSTM, or BERT for sentiment analysis, often staying within either the traditional machine learning or deep learning paradigm. For instance, Wilson et al. 2024 study compared logistic regression and LSTM for analyzing ChatGPT-related tweets, but notably excluded transformer-based model like BERT or Roberto. Our research aims to bridge this gap by conducting a more comprehensive comparison across both traditional and modern approaches. Next, the research process begins with data collection, where we gather 290,294 sentiment-labeled tweets related to ChatGPT from Kaggle's data repository. Each tweet in this dataset was annotated with one of three discrete sentiment labels: good, bad, or neutral. Moving to data pre-processing, we implement a comprehensive cleaning and normalization pipeline consisting of several case states. Text normalization was our first focus, where we strip URLs, HTML markup, and encode entities using regular expression. Standardize English contractions, converting such as its to it is. Remove metadata indicators like hashtag mentions and retweet dictionary. Normalize non-ASCII characters, punctuation, and white space. Eliminate tokens shorter than 2 characters to reduce noise. Applied a sentiment-specific dictionary to standardize informal language and slang. Mapping variant like GR8 to grid. We then perform stop words removal, utilizing the analytical stop word list to eliminate the common words like the and is. This step was crucial for reducing noise and focusing on words that carry meaningful sentiment. The process continued with lemmatization, where we applied specialized rules for lemmatization. Use a verb lemmatization dictionary to ensure consistent word forms. Perform text cleaning by removing duplicate tweet based on a first occurrence resolution strategy. Eliminate AI-related terms from the dataset to prevent bias. Next, let me detail our ADA findings through our histogram and word cloud visualization. Our histogram revealed distinctive distribution across the 290,294 tweets. V4 preprocessing histogram shows a right-skewed distribution with multiple peaks. Highest peaks occur around 100 to 150 characters. Negative tweet clustered around approximately 129 characters. Positive tweets show a longer distribution, approximately 189 characters. Neutral tweets centered around mid-range, approximately 155 characters. Notable outliers extending beyond 250 characters. After preprocessing histogram or normalized distribution with reduced skewness, primary peak shift left to 50 to 100 characters. Negative tweets average 56 characters. Positive tweets average 90 characters. Neutral tweets average 70 characters. Significant reduction in outliers and extreme values. Next, the word cloud complement our histogram finding. Negative sentiment word frequency not dominate with 13,000 occurrence. Neutral sentiment common term get like axe. Positive sentiment dominant word use right good. This visualization demonstrates how our preprocessing reduces average text length. Next, step 4. We perform data split and feature extraction, where we carefully divide our dataset using a stratified sampling methodology to preserve class distribution. The data is split into 3 sets: a training set of 70%, a validation set of 15%, and test set for 50% too. For feature representation, we employ FVDF factorization for MML model, while our deep learning model use various tokenization strategies specific to its architecture. Moving to step 5, modeling, we implement 2 categories of model. First, machine learning models. We use logistic regression, SVM, life bias, and XGBoost with the hyperparameter tuning. Next, deep learning model, we use LSTM, CNN, BERT, and Roberta with hyperparameter tuning too. Finally, in step 6, we conduct evaluation, where we assess model performance using multiple metrics: accuracy, precision, recall, and advanced for across sentiment classes.
Okay, so first thing first, I would like to discuss about the result for the class bed or the negative sentiment class. So the best performance for this class is Bert and Roberta and CNN with a high F1 score of 0.91 for Bert and Roberta and 0.89 of F1 score for CNN. For the medium performance, we have logistic regression model, SVM model, and XGBoost model, and the lowest performance, we have knife Bayes and LSTM models. So for the key insight, all models show high recall for negative sentiment. Transformer models have the best balance between precision and recall, and LSTM has perfect recall but very low precision, indicating that LSTM might overpredict of some of the negative class. And for the next result, we will be discussing about the class neutral. So the best performance for this class is again Bert and Roberta, and also CNN, with the F1 score of 0.73 for the transformers based models and F1 score of 0.65 for CNN. And for the medium performance tier, we have logistic regression and SVM. And for the lowest performance tier, we have XGBoost and LSTM models. The key insights for this class is that the neutral class remains the most difficult to detect for all models. And the transformers model shows significantly better performance than other models. And the traditional models struggle with low recall. And moving on to the good or the positive sentiment class, the best performance for this class is Roberta, Bert, and CNN. The medium performance tier in this class is logistic regression, SVM, and XGBoost. And the lowest performance tier of this class would be knife Bayes and LSTM models. The key insight that we get from this result is that the transformer models show the best balance for positive sentiment, while CNN has high precision but low recall, and LSTM again fails to detect this class. And for the conclusions of our research, the first one is that transformer-based models outperform traditional models. These include Bert and Roberta. So transformer-based models, particularly Bert and Roberta, achieved the highest accuracy and F1 scores. And the second conclusion is neutral sentiment detection remains a significant challenge. All models, including Bert and Roberta, struggled with the accurate classification of neutral sentiments. And the last conclusion would be traditional models are still competitive. As we can see, logistic regression and SVM performed robustly with accuracies of 0.79 and 0.77, respectively. While they are computationally faster and simpler, they lag behind transformer-based models in capturing emotional subtleties. And for the future works, the first one is improving neutral sentiment detection with modern BERT with the objective to leverage modern BERT's long context processing capabilities to better classify neutral sentiments, which are often ambiguous and context dependent. The approach is to use modern BERT's ability to handle longer sequences to analyze extended conversations, and to fine-tune modern BERT on datasets with a higher representation of neutral sentiments to improve its performance on this challenging class. And the second proposed idea would be to use multimodal data integration with modern BERT. The objective is to enhance sentiment analysis by integrating multimodal data using modern BERT's advanced architecture. The approach will be to combine modern BERT with multimodal transformer models and to use modern BERT's attention mechanism to capture emotional cues for multimodal modalities, such as emojis, image, or tone of voice. And here are the list of references that we use in our research. And thank you for your attention, and we invite you all if you have any questions or feedbacks. Once again, thank you very much.